Okay. Good morning, or actually good afternoon all now. I'm going to start here with something that broke yesterday that I truly believe we all need to remain abreast of. And I just updated CISS100.com with this information too. So yesterday, there were Senate hearings with Facebook and Twitter. And these were follow-up hearings from big tech on with the Senate hearings with Google, Facebook, and Twitter. So I did create a new page here, and I extended. We saw earlier this semester, the problem with how Google and Facebook are directing us, profiling us and directing us to information in 2012 is what it's thought to be, information it thinks we want to see, but that is now changed. Yesterday in Senate, it was revealed that Google, Facebook, and Twitter actually created an internal application where they track us. They not only track us, but they share this information between Twitter, Google, and Facebook. And they use this information to censor information from us, but also direct us to information they want us to see. Not what they think we want to see, but what they want us to see. This is concerning. And please note, this is not a political statement at all, okay? Many of you know I was United States Navy Sea Air Rescue Corpsman. And in my service oath, I swore to uphold the Constitution and therefore the First Amendment, free speech. And I also swore to uphold the office of the United States President, regardless of who it is. That's in my service oath. And these are follow-up, hearings. And 2 weeks ago, it was revealed, Twitter, as an example, they didn't censor Iran's Ayatollah, who repeatedly stated the Holocaust was fabricated, it did not occur, and urged people to murder and be violent against Israel and the Hebrew nation. And yet Twitter censors the United States president, okay? Regardless of whether you agree with the president or not. Again, my service oath was to support the US president, to support the US Constitution. And it's now been revealed that Twitter, Google, and Facebook collude to share information, to track us, and share this tracking information, and then censor us from information and direct us to the information they want us to see. This is really concerning. Of course, it has democratic implications, but also just as an academic or a scientist, I need to be able to find all information for proper assessment. So I'll leave it at that. Hopefully everybody will remain abreast of this because it is concerning. So back to lecture module 11, program development lifecycle. Okay, we're going to see a lot of similarities with the system development lifecycle. The way the textbook presents it, it presents the program development lifecycle as kind of the waterfall method, but really, we really should be approaching it from an iterative perspective, similar to what's best in system development lifecycle as well. And we see the 5 phases, so the problem analysis, the design, the coding, debugging and testing, and implementation and maintenance. And there should be some iteration here. For those of you in Programming Logic 1, you know that when you code a program, you're compiling it, you're debugging it for syntax errors, things of this nature. So again, there is this iterative mechanism taking place. So let's take a look first at the various phases. Okay, so the analysis phase of the program development lifecycle. First, we begin with the problem analysis. What do we need the program to do? We're actually going to start to think about the specifications. What should the program do? What are the possible inputs? What are the possible outputs? We're not completely constraining it as we'll do in the design phase, but we begin to think about these things. We think about the environment, various platforms, just as in the system development lifecycle. The output from this phase, the documentation, and here too, again, you'll hear me call them deliverables. In some textbooks, you'll see them cited as deliverables rather than the documentation. The output from the analysis phase will be the program specifications. And a note on this, we strive to get this phase correct. We try to incorporate or acknowledge every feature that must be included. What we're trying to inhibit is feature creep, to where down the line, oh, we also need this, we also need this. Now again, some of these may come from external factors. You know, we're writing or creating a program for some company. It was, you know, conceived by the CEO. And that CEO will be out on the internet and see some functionality. Oh, that'd be cool. Can you also do this? And if we catch it in the analysis phase, yes, we can. It's very easy. The problem comes with feature creep in subsequent phases. Because as we start adding things on, you know, hammering on add-ons, we may introduce vulnerabilities. So we strive to get this analysis phase correct and have complete program specifications. These program specifications will be used as input into the design phase. In the design phase, we take the program specifications and flesh out what's the algorithm going to be, what's the process going to be, okay? There's many tools that we use for this. In procedural programming, we use control flow diagrams, pseudocode, and hierarchy charts. We do this in object-oriented design as well, but we also use unified modeling language. So we add this on in object-oriented design, and we'll take a look at this as well. So structure charts, we saw this up above in yesterday's class. I'm saying up above in the presentation. When we saw procedural decomposition, right? It's typical that a program will have a, you know, input module or several. It'll have initialization cycles. It'll have output modules. It'll actually have the modules that will, you know, encode or contain the various processes that must take place. So we'll have structure charts as was presented yesterday in procedural decomposition. When we look at, say, flowcharts and pseudocode, they graphically, step by step, show how the algorithm should proceed. So let's take a look. Here is a control flow diagram. Now, we're seeing two new symbols here. Previously, we saw these up above, or yesterday, in the control structures. We know that blocks or rectangles are single statements, or maybe several sequential statements, because I can abstract that very well. Now, in the program development lifecycle, in the design, as a design tool, I could have a complete method here, module, something of this nature, because I could abstract, well, we're going to do this next. We're going to get input. That input may actually have a loop in it, right? While not end of file, read the input. So we may perform that abstraction and contain many things in a single block. But again, note that single block will have a single entry and a single exit. And we strive to do that with all of our structures. Of course, the diamonds were introduced yesterday. They are decision structures. So we have decision structures, of course, in the simple if then else selection. We have them in the repetition, but we actually may have them in modules too. Get more input, do some processing, go back and get the next record, okay? So in a bigger picture, we may actually have repetition on a grander scale. What's new is the start and stop symbols that we see here, but also the parallelograms. Parallelograms indicate input and output. So if we've traced through this, we can actually see how execution should continue. So this is one tool. It's very good for presentations. It's great, you know, in a boardroom to show how things will occur. From a programming perspective, though, turning this into code, I tend to prefer pseudocode. Pseudocode is just a generic type of algorithm. So you see my indentations, just standard do whiles. The specific programming language we choose may not have a do while, it may just be while, okay? But it's very readable. In pseudocode, of course, we don't have any syntax. But again, If you're in Programming Logic 1, CISS 110, or even Python 109, I could hand this to you at this point in the semester, and you could probably convert it into code. Very straightforward. It really supports teamwork because you can design the teams. I could hand this off to someone very easily. Now, object-oriented design. I mentioned yesterday, object-oriented design is based on 3 principles: encapsulation, inheritance, and polymorphism. And I'm going to go into those in just a little more detail today. Again, it's not in the textbook. What is encapsulation? Well, we showed yesterday the class structure. We actually saw this last week in UML and Systems Analysis and Design. So here I have a class for bicycles. I have attributes, which variables, or methods, which are the behaviors. So I'm encapsulating everything that it is to be an object within this structure. And this is actually, again, the way that we look at the world. I see an object, it has attributes, and of course it may have functionality or behaviors. Recall, the class is the blueprint, it's the architecture. Yesterday I used the example of what color is a Jeep, and you can't answer that. It's not until you actually have a specific instance, what color is that Jeep? It's blue. Okay. I can ask the question, what color is a person's hair? You can't answer that. It could be blonde, it could be brown, you know, no hair. It's not until we actually have a person, me, a specific instance, a specific object, an instantiated object that I can say, what color is my hair? Brown. What color are my eyes? Okay. The state of my object is encoded in the attributes. Now, this encapsulation supports security. Why? Because the attributes of an object, class, they're defined in the class, should be private. You should not be able to directly act on them from the outside in your code. Those of you in Programming Logic 1 know what I'm talking about, and I apologize for those who aren't. But consider my example with me as a person. You cannot change the color of my hair. It's private to me. I could dye it myself, right? That would be in my behavior. I could do that, but you cannot. Consider another example, a bank account. Okay, a bank account, what does it have? It probably has a balance, and it has specific actions that you can perform in defined methods. The bank actually establishes the permissible interactions with that account. That account better be private. If that account isn't private, I could hack in there. Account, you know, balance gets balance plus 1 million. I just hacked my account and added $1 million digital dollars to my account. But that account balance should be private. The bank will provide public methods that I can use to interact with it. It will define what it is to deposit, withdraw, check the balance. Just fleshing this out further, what would it mean to deposit? Well, the bank will define this process of, well, it takes in your money, takes in your checks, counts the money, verifies the checks don't bounce, and if everything's okay, it will increment your balance on your behalf. You're never allowed to actually interact with that private attribute that is the state of your account, right? And by the word is the state there, the state of an object. We actually saw this in Linux Lab 9. Hopefully, you took my recommendation and took a snapshot of your running Ubuntu operating system. What did it do? It captured the state. So it captured the operating system as it was installed, any settings, you know, username, passwords in the password file, things of this nature, any applications you may have installed. So it was the state of that running system at that particular time. In this case, that state is a virtual because it's a file, right? It's just a file that contains the operating system, all the applications and any whatever settings were in there as well. Okay, so object-oriented design, encapsulation, inheritance, polymorphism. We covered encapsulation. Encapsulation supports security. Okay, inheritance. Inheritance, of course, is a structure. We're talking about a parent-child relationship over and over, okay? Ancestors. We go from the generic to the specific. We see this in our biological classification system, right? Kingdom, phylum, genus. So as we move down that tree, that biological classification tree, we get more and more specific. This is the same principle in object-oriented design. What that supports, which is one of our primary tenets in software development, code reuse, right? If I don't have to reinvent the wheel, if there's already a class out there, but I need just a little more functionality, I'm not going to modify that existing class. I'm going to make a child class that inherits all of the attributes and behaviors of the parent class. And then I may create something new, or I may override them, just change them just a little bit, you know? And typically at this point, you know, in class, I get to see students and, you know, they're falling asleep. This is kind of dry stuff until I say the word game design, game programming. Everybody perks up. This is what's used in game programming. Think about what occurs with each successive iteration in games, okay? Yes, there are advances in graphics and things of this nature, but really what's happening is you're increasing functionality. Are they rewriting the game from the ground up? Not if they've implemented their system, object-oriented system with inheritance properly before, no. I'll go back to, just because it's easier to describe this from a 1990s game. You know, 1990s, it was, you know, a big deal when a player would get a flamethrower. It wasn't in the previous incarnation of that game. You know, they had swords and axes, things of this nature. Well, think about what would occur. It's still going to have all of those swords, axes, you know, weapons, but now I create a subclass to where, you know, a child class, excuse me, it's a better way to say it, where they actually have use of a flamethrower. They added one little thing and they get to, again, charge people for the new version of it, okay? So that's inheritance, encapsulation, inheritance. Lastly is polymorphism. And I'm going to present this quickly. And if you're in Programming Logic 1 and you should be getting to arrays right about now, poly means many, forms means, morphism means forms. So many forms, polymorphism, many forms. We have this inheritance hierarchy. Maybe the parent class, a player, has the method move defined of how it moves on, how the player moves on screen. Maybe they're monsters. They also may have a move functionality. And maybe in the latest version, a player can get a special, you know, hyper warp, whatever, I'm making this stuff up, move functionality. And I put all of these objects into an array. And I iterate or repeat loop over the array where the index changes, dot move, and I call the new method, and they all move, okay? Even though there are many different forms, monsters, players, different versions of players, they all have that move method defined, many forms, and everything works, okay? So, design tenets. By the way, the word tenet just means principle, design principles. Good design is paramount, okay? For code sustainability, to continually update it and maintain it, it's absolutely imperative. So, first of all, we should test everything. We should have thought about this back in the problem analysis and the design. Hopefully we did. And it's almost impossible to do, to think about every eventuality. We do follow the one entry point, one exit point rule. So I don't want multiple return statements out of functions, procedures, and methods, things of this nature. I want to be able to deterministically really determine where the execution is going. Other things you should know, you know, no infinite loops, logic errors, of course. I won't say anything more about that. Documentation. Documentation from the design phase will be all of the design specifications. You should be able to hand these design specifications over to a coder or a team of coders, and they should be able to implement them. If they come back and have questions, okay, it's quite likely that your design testing wasn't specified in its entirety. We do this with desk checks and trace tables. Okay, program coding, third phase. We now have the design specifications, and my dogs have someone at the door. we need to choose a programming language, hopefully in accord with the domain. Is it a scientific computing domain? Are we in AI, etc.? We need to make sure that it integrates with other applications, integrates with our platforms and environments. Often overlooked, not by businesses, but by people coming into the field, is programmer availability. There are many great programming languages out there. You know, these boutique style programming languages, Ruby on Rails, Groovy on Rails. Very highly powerful. They're great, okay? Rapid application development, or they facilitate rapid application development. But those programmers are scarce. God forbid you have a critical application, you know, you're constructing, you're coding, and you lose that programmer, or later on in the maintenance phase, you lose that programmer. Is that program now completely unsupported? I have to go out and find a Groovy on Rails programmer. They may not exist. They may be very expensive. So it makes sense to understand your local environment too. I know that I can find Java programmers everywhere. So Java can be, you know, kind of burdensome to work with, but I know I'm always going to have Java programmers at my disposal. So it's kind of nice to know that. Standards for the company in terms of documentation, in terms of variable naming, are using camel case notation, things like that. So just these conventions, it makes for more readable code, more maintainable code. Again, when people come in, you're going to lose people. It's going to happen. People are going to leave your company. You want to bring people on board. You want to get them up to speed as quickly as possible. You don't want them taking months just to understand the code. So documentation and coding to standards. So, spoke about this. We strive for reusable code, always. Okay, we don't want to reinvent the wheel. And as soon as you say this, reusable code, object-oriented design, inheritance. Okay, so here's one of the driving factors that has really driven many organizations to really pursue object-oriented programming. There are instances where that may not be appropriate. Embedded computing, object-oriented programming, you know, does not run as quickly as just straight procedural imperative programming constructs. So know that too. Scientific computing, real-time computing is probably best done in procedural computing if there are time constraints. The output from this phase is the documented source code. And don't undervalue the word documented, okay? Source code without the documentation, especially if it's millions of lines of code, you know, it can be useless because you may never be able to upgrade it, maintain it, etc. We'll do that coding example. Code generation, okay. And again, we've looked at some of this before. I've introduced this before. We know about assemblers. Assemblers are more straightforward than compilation or interpretation. Why? Well, assemblers, of course, have that one-to-one mapping between the assembly language and the machine language. So it's relatively straightforward to convert assembly language to machine language. Not so for compilers. I gave the example yesterday, y gets x plus 2, right? It's a high-level language. But minimally, that would be converted to 3 machine language instructions. I would have to move x to a register, 1 cycle. I would have to add 2 to that register's contents, another cycle. And then, of course, I'd have to save it back out to the variable location that y points to. 3 cycles, 3 instructions. So naturally, compilation and interpretation is going to be more complex than just the one-to-one correspondence of assembly language. What's the difference between compilation and interpretation? Compilation is static. As soon as I say the word static, you know, before runtime. So I compile a program, it becomes machine executable, of course, before it's run, and then when I can run it. Interpretation is dynamic. You actually have the high-level source code on your machine, and as you execute it, each line in turn will get converted to the corresponding machine instructions. This must be done over and over. So I'll use the example of Microsoft Office. Microsoft will compile Microsoft Office, and they'll distribute it, say, on DVDs. Maybe you download it. So I'm not talking about the web version. They did this compilation once. So the millions of users out there using Microsoft Office don't have to reconvert it from high-level source code to executable code. In contrast, if Microsoft Office was interpreted, they would distribute the source code. Now, of course, Microsoft does not want its proprietary source code out there. But if this were the case, every time you run Microsoft Office, your computer would convert that high-level source code, high-level language, to machine instructions over and over, every day. Every day you used Microsoft Office, it would reconvert that. Multiply that by the millions of users. Obviously, from a global perspective, that is consuming far more compute cycles. Why would we ever choose interpretation over compilation? Well, security. Compilation, Microsoft, ActiveX. You've probably done this. You've probably downloaded something that had an ActiveX component, Netflix. And you were asked upon installing it, do you allow this application to do this? Essentially, Microsoft's washing their hands. The onus is on you to assess whatever you downloaded and execute it. Should it wipe out your hard drive? Oops, not our fault. You said yes. Interpretation. Interpretation, you're getting the source code. Your computer can actually look at the big picture. Recall the fetch execute cycle simulation I did, right? The CPU is just executing these tiny little microcode statements, right? It's moving little things around. It has no idea when it moves the read-write head to location 0 and starts writing zeros that it's essentially erasing your hard drive. Interpretation. You get that high-level source code. It says essentially can be inferred or semantically assessed. You're erasing my hard drive. No, stop. Don't permit that. So consider what I presented yesterday with Java. Java arose in the early 1990s by Sun Microsystems for heterogeneous embedded systems. And then the internet arrived, which is characterized by heterogeneous systems. But what else is important for the internet? Security. Okay, ActiveX again puts the onus on the user. Do you allow this to happen? Okay, anything that goes wrong, it's on you. Java, applets at least, were interpreted. So the Java virtual machine, the Java runtime environment could see what was taking place. You want to erase my hard drive? No, you're not permitted to do that. You want to download my contacts? No. So there's enhanced security with interpretation at the cost, of course, of efficiency. Okay, looking at code generation, specifically from a compilation perspective, we have the high-level language, the source code. It will be compiled into object code, but it also needs to be combined with other object code. Again, for those of you in Programming Logic 1, you know you're importing packages. You're using the methods, the functionality in those packages. In C, of course, we're including libraries. Same thing. So your high-level object code is getting combined with essentially library or package object code into a executable program. At some point, it will be loaded into memory, right? Program becomes a process and executed. But that load module itself needs to be relocatable, which means the addresses need to be relocatable or be offsets, okay? They're not precise addresses. So as an example to show why this is necessary, consider you run Microsoft Office. First thing, you boot your computer, you run Microsoft Office. It's quite likely Office gets loaded into the lower portion of memory, right? The first contiguous bytes. The next day, you start your computer and you load a browser. You load a bunch of other iTunes, a few other programs, and then load Microsoft Office. Obviously, the operating system quite likely will put it into a different place in memory. So that code needs to be relocatable, and that's done with offsets. Moving on to the debugging and testing phase. Again, You know, the textbook says this, okay? Those of you in programming or have done programming, know you're debugging as you code, okay? You know, we try to catch syntax errors. We'll catch syntax errors first because the compiler will spit them out. If your program is not in accord with the high-level language's syntax requirements, it will not compile. So first, it must be syntactically correct. Moving on, we then need, it's up to the programmer to make sure it is semantically correct, okay? Logic errors. For this prescribed input, does it produce the correct output? And we'll create test cases, okay? We'll test it on various subsets. Of course, we can't test it on everything. That will come in time, alpha and beta tests, and we'll get there. Now, it's very important that as you test your program logically, you actually keep and maintain the testing inputs that you provided and the corresponding outputs. Because we're going to see down the line in Agile and Extreme Programming, we're going to continually run these. As we continually make modifications or enhancements to our program, adding functionality, we don't just test the new functionality, we also have to test the old functionality. So we have to make sure that the program is consistently robust. Okay, so testing, again, many things, you know, simple ones, divide by zeros, things like that. And various programming languages have different ways of managing this. You know, Java uses exceptions, things of that nature. And I won't go into those specifics because I'll leave that for Programming Logic 1. When we look at testing, though, we do recognize two distinct phases, okay? Alpha tests, internal on-site. Of course, the programming team, the coding team is continually testing. But most companies, larger companies, will also have Q&A, quality assurance tests, and they'll turn the program over to the quality assurance team, and they will test as well. And they'll not only test with prescribed valid inputs, they'll probably test with invalid inputs. This is quite often what hackers do too. Hackers, and we'll see this in the last week, we'll look at some advanced topics, one of which will be hacking. Hackers will try to break a system. They'll provide a system with inputs it does not expect or even does not recognize. Because if they can break it, they might be able to find a vulnerability. So, and we'll look at this in the last week of class. So the alpha test is internal on-site. Beta tests may be for a specific population, or release it to some like developers, or, you know, as Google Chrome often does or did, I don't know if they're still doing it, they'll release their beta versions out to the community. They'll just let the community crowdsource it, see if they can find problems with it. And of course, they're not telling people that's what they're doing, but essentially that's what they're doing. You actually have the opportunity to engage in continual beta testing too. Quite often when you install things, you'll see, you know, it'll ask you if you want to send feedback to the company. Okay, what's the feedback? Your logs, okay? So to help them with their continual improvements in the beta testing. So testing documentation, at the end of this phase, you have the completed program, copy of all test data, test results, and finished program. Moving on to the most expensive phase of the PDLC is the implementation and maintenance phase. Why is it the most expensive? Well, recall, you've sold the product. It's out there. You're not getting any additional income from it, but it may need security patches. It may need functional enhancements just to remain competitive with what's taking place in the environment. There are always new platforms out there, you know, new devices that you may need to take in account of. So very costly. You're paying these people to maintain your code, but you're not getting any additional money from it. When we look at PDLC, Program Development Lifecycle tools, there are many. I'll move through these rather quickly. And again, when we look at the Program Development Lifecycle, we're looking at software engineering. We're looking at managing, you know, the entire cycle. So again, I'm taking myself kind of up a level. I'm not just looking at coding or the designers or the maintainers. I'm actually looking at the entire process. So there are application lifecycle management tools. Kind of a bare bones one is present in one of the final projects in Eclipse, the Extreme Agile Programming final project. I'm going to talk about that in a minute. But Eclipse also has plugins that greatly enhance its application lifecycle management capabilities. And again, I'll talk about this in just a minute. One of the things over time, of course, we are continually testing, maintaining, enhancing. And again, we maintain all of our test cases. Because when I add a new functionality, I don't want to just test that new functionality because maybe that new functionality did something to the rest of the program, the way it interacts. I need to test the entire program again in its entirety. I may have 1,000, 10,000 test cases. I don't want to do this one by one with keystrokes, right? I want the application lifecycle management tool to run all the test data, all the particular instances against the program with a click of a button, a single button. And to some extent, I can do this with macros, things that, that record my keystrokes. But really, optimally, I want to do it with an ALM tool. So I continually document, okay, the requirements. I continually document basic configurations, all known configurations. Document everything. Again, you never know what's going to happen with your workforce. You lose a vital team member and you have to bring someone new on board, you want them up and running as quickly as possible. Just a quick note on application generators. They're out there. They're graphical design units you can drag and drop. Be very wary of these, please. These integrated development environments that have application generators may have security vulnerabilities built into them. And it's not on purpose. It's not done on purpose. It's just they didn't think everything through. A case like this happened just a few years ago with Experian. We know Experian's a credit agency. And the software they developed in-house by Experian used an integrated development environment that had, when it did this code injection, code generation, it introduced a vulnerability. And the programmers never noticed this. They just used, look at that, it's done, great. They moved on, and they compromised millions of records, if I recall correctly. So when it comes to application generators, integrated development environments, be wary. It may implement something for you, but don't take it as certain that that is, perfect code. Eclipse, again, which is one of the final projects I'm going to talk about in just another second, has some code generation, although it only generates code shells. It actually doesn't generate any logic, things of this nature. But again, I recommend if you use this, Eclipse, don't trust it either. Use it. It'll greatly enhance your functionality and your efficiency, but don't just heavily depend upon it. So other device software development tools, about, again, if you're in Program Logic 1, you know about software development kits. You install the Java SDK on your machines. So I won't say much more about that. There are SDKs specific for mobile computing. Application program interfaces. Recall, there are 3 types of interfaces in computing. User interfaces, right? Like my keyboard and my monitor here. I have software interfaces, software talking to each other, web services, things of this nature. And I have hardware interfaces, ports, Ethernet ports, USB ports. And recall, you actually saw this in your Linux labs, okay? With pipes and redirection. You pipe the output from one program into another, okay? It's a very general, basic API, but that still exists. By the way, this is also the Java import packages, just so you know. Rich internet applications. We presented these back in chapter 8 in internet. So the ability for software to appear to be on your desktop, but it's actually running essentially from the cloud, from the web. And there are many variants of this. Some actually do require that internet connection all the time to operate. Others, Google Docs now has complete offline mode. It will run local to your computer without an internet connection. Which leads us to, lastly, Agile and extreme programming. So again, I'll introduce one of the final projects today. I'm going to introduce them all next week when we fully get into them. I will say again, please be through Linux Lab 11 this week. I've never had a student not complete the final project in its entirety if they have the full time to do it. And really, many students do it very quickly and are done with it in advance, okay? If they've done the preparation. Now, some students will fall behind the Linux Labs and they will get through Linux Lab 11 this week, but they've kind of done it rapidly the last few weeks, so they've missed important points. They may have some challenges with the final project, but if you're through with Linux Lab 11 this week, again, you still will, I guarantee it, complete the final project. So one of the final projects is the Extreme Agile Programming with Eclipse and Java. And this is highly recommended if you know you're going into programming. You will need an IDE. It will become your best friend. If you're going on to a four-year school in computer science, software engineering, you will have a course in systems engineering or systems design. You will write maybe an entire operating system, a minimal one, or components of an operating system. You will need something to facilitate this, going beyond just the Dr. Javas of the world. You really want something, application lifecycle management. Now, Eclipse is a wonderful tool, and the tutorial that you will work through in the final project will teach you Agile and Extreme Programming. What is that? Agile and Extreme Programming strives to maintain functionality, a current program, through small incremental changes. Does this with rapid application prototyping, rapid application development, things like that. It really embraces an iterative approach as was presented in the system development lifecycle. You've seen this. At least you've seen the end results of this. Your mobile applications. How often do your mobile applications have an update? I've noticed less frequently now, okay? Or maybe it was back when I was on Android. And I was on Android throughout the 2000s. I didn't move to Apple until, say, 2013. And I noticed some of my applications updated nearly every day. How are they doing this? Through Agile and Extreme Programming. Small incremental changes. Now, when you do this, of course, you need almost all 5 phases and need to run through all 5 phases recurrently on a daily basis. How do you manage this? It's especially important for your test data because you continually build this test data more and more and more. You add a functionality, well, you test that new functionality, but now you have all of these previous test cases you also need to run. You need a management tool to do this. Eclipse will provide you with that management tool. It also provides you with visual debugging, things of this nature, step debugging, trace debugging. So it's a really nice tool. So again, if you're going on in computer science, software engineering to a 4-year program, if you plan to just go out and work after 2 years, a lot of shops out there in New York State use Eclipse. GE uses Eclipse. So it really will pay dividends for you to become familiar with it now. You'll probably never use anything else if you go into Program Logic 2 or Advanced Java or anything else. And there are plugins in Eclipse for Python, XML, HTML, all of these things. So I highly recommend it if that's your focus in your future. That's all I have for today. So if you have any questions, of course, please let me know. Please do everything you can if you're behind to catch up and get through Linux Lab 11, but don't skimp on the reading either. And Linux Lab 11 does require, you will be required to go back, likely, into previous Linux labs if you've forgotten that content. It's kind of a way to self-assess your preparedness for the final project. That's all I have. Have a great day. Have a great week. Thanks.
Hi, Mr. Luby.